Hello, today I'll be presenting my IMSE 514 final project where I will be discussing about the prediction of churning customer data or retaining customers using backing data. And so let's begin. So before we begin, let's talk a little bit about the data description. So the data was obtained from Kaggle.com. All of the references will be in the report. It consists of 19 features, one index feature, and one target label. The index feature basically uniquely identifies each row and hence will be not used in any of the analysis moving forward. The target label is the attrition flag, which I will explain a bit more in the next slide. We have a bunch of features, some of them continuous, some of them discrete. Discrete but categorical features refers to features which are discrete and are categorical in the sense that education level starts from educated up to postgraduate. Income categories are in brackets, and card categories starts from blue and goes all the way up to platinum. So there is technically an increase, and hence I have classified those as discrete but categorical because there could be a correlation. Because you would expect like fewer platinum card holders than blue, and that is important to know. And then we have simple categorical features, which are just the gender and marital status, because there is no real way to put them on like a scale, so to speak. So moving ahead, we have the actual attrition flag, the target label. So the target label, it's we have around 10,000 customers. We have out of which we have 8,500 customers which we know are not going to leave the bank. And we have 1,600-ish customers which are at risk of leaving the bank. So the goal of this data set overall is that a bank wants to identify customers which are at the risk of leaving the bank or at risk of churning or attrition and identify them so that they can engage them in retention tactics, which includes targeted advertising, phone calls, offering them special offers to stay, like credit card deals, and so on. But the important thing here is that identifying the attrited customers are much more important than identifying existing customers, which hence so that we cannot, given the data imbalance here because it's not a balanced class, it means that we cannot just use accuracy as a suitable metric. We will have to use some other forms of other metrics which will help us increase the performance on predicting the attrited customer class. Hence, the recall of the attrited customer will be the best option here. And also, additionally, we don't want to increase the recall of the attrited customer class at the rate of like losing other metrics for existing customer or the overall accuracy. Because if we predict everything to be attrited customer, we will score quite well on attrited customer, but we're gonna kind of defeat the purpose. So apart from recall, another important metric that we will be looking at is the F1 score, because the F1 score is a combination of precision and recall, and hence it will give us a good idea of how the model is performing overall. Accuracy will not be considered because it's honestly not the best metric to use here. So let's look at the features. So the first thing we have to do is do a data analysis of the dataset to understand what the features look like, how the features behave, and how do they relate when it comes to the target label. So another way to look at this would be feature selection and correlation, which we will also be talking about moving forward. But to first to begin with, this is to just build a general idea of what the data looks like. And when it comes to that, so you'll see that the first 5 or 7 diagrams are graphs are continuous, and while the rest are discrete. But the main thing we're trying to look at here is blue refers to the like the existing customers, while orange refers to the attrited customers. What we should expect generally what happens is when it's the distribution is normal and there's no variance, we would see a similar distribution existing between both the existing customer and the attributed customers. Any change from that, so if there's a variance between the existing customer and the attributed customer, that is what we're actually looking for, because that actually gives us more information about how well a feature can determine what your target label you might apply to a given customer. Uh, these, all of the ones you can see here, all 16 of them, they don't have a strong correlation or variance or however you want to see it, in the sense that they have a very uniform distribution. So it's not likely that you would extract a useful number of, you could say that there's a high entropy, so to speak, if we're going to talk about instances of freeze. But moving forward, like these are three graphs which I feel is more interesting. And that is because if we look at them, let's look at the third one to be more specific, which is the total transaction count. The total transaction count, the distribution of existing customers has two peaks. It's not unimodal, it is most likely a bimodal distribution. However, the attributed customers is a unimodal distribution, and they fall primarily under the first peak of the data, which allows us to understand that more customers present in the second peak are less likely to be attributed customers. This is very important because this helps us. This means that this feature is very useful when it comes to determining the feature selection, or for good for the possibility of getting good results when we even use machine learning later on to see how well the model behaves. You can see that also in the other two graphs, but the general example is the same. Like there is not following the same distribution as our existing customers, and hence we are getting more information from these features. However, these are mostly visual examples, and these are visual graphs. They don't give us a concrete idea of what's going on. So we have to try and look at some other approaches as well. So for that, we have the heat map. So the heat map's quite complicated looking right now, but what we're going to focus on mostly for this is the circled region right there. And that is because the second column and the second row is the attrition flag, which is a target label. And we want to see which features have a high correlation with the attrition flag. Why? If there's a high correlation, it probably means that if I know what the value is in one of the features, we have better knowledge of what the target label will be. So having a high correlation is always good. They usually form the best features as well. The only unfortunate downside here is none of the features have a strong correlation with the attrition flag. Most of them top out at around 0.37-ish at most. That's like the highest. And there's another one I believe which is 0.32. But from that, it's not the best performance, like not high correlation, which means that it's not going to be easy to do a concrete feature selection. We will have to probably use all the features for this, especially given the fact that it's very imbalanced data. So we want to use as much information as we can get, so to speak. So these give us more solid numbers, so to speak, between the target label and the features, which we can then use to establish what might be the most important features. However, the best way, or one of the best ways, so to speak, is to use some lasso cross-validation. I have also used recursive feature elimination, which I have talked about more in the report, and I will talk about it a bit more right now as well. But the results of lasso cross-validation are much more quantifiable in a chart and experiment presentation, so we'll talk about that more. So in lasso cross-validation, we basically find out which features have the most significance. And as you can see in the chart here, we have increased them in degree as an order of significance and by proportion of like how important it is. And you will see that total transaction count and total transaction amounts They also have correlations with each other, interestingly, but you might have seen in the graphs before. Those are the ones that we saw to be having a difference in variance and also have high correlation, which all adds up to the hypothesis saying that, okay, yeah, these are the most important features. And so these are like ordered in like what are the most least important features, and they're not they are useful if you had a much larger data set. Here we only have 10,000 rows. But however, if we had like a million or a billion rows, then feature selection would be helpful because it would reduce model complexity. Here, because we are trying to, after all, like target for a minority class, we will not be applying feature selection, and I will also later on show that feature selection actually does harm the results slightly so than just using all the features, which is expected. And quick mention to recursive feature elimination. It is another three-way method for feature selection where we just recursively eliminate features until we get left with the best performing ones, and then we rank them and we can use them. So again, more on that will be in the report. That brings us to supervised machine learning, the actual classification part. So the problem that we have identified here is going to be a binary classification problem where the target label is attrition flag, which has two classes, 0 being existing customer and 1 being the attrition flag. The attrition customer. And our goal is to identify attrition customers, and the priority is to identify them to ensure customer retention. So I have gone through 4 steps here, and they are: first we apply the basic approach where we try some basic machine learning models, KNN, tree, logic regression, naive Bayes. These did not work well, and the primary reason for that is that the classes are highly imbalanced. So what will end up happening is you will get quite good accuracy on the majority class, but on the minority class, you will have very poor recall, and because of that, the F1 score will also collapse, and that is not what we want from the results. So the basic decision trees, you'll see the results also coming up, are not the best solution here. Then we move on to ensemble modeling. So ensemble modeling is one of my personal favorites when it comes to using supervised machine learning models, where we use not random techniques, we use models like random forest, gradient boosting, bagging, and voting. Gradient boosting being my personal favorite, and we're going to see very quickly why. So the voting here uses the ensemble models in a soft voting method, so that we can expect the best of all worlds, hopefully. And we do get that to an extent, but we will look at that more. So ensemble method models will perform much better than basic models, but maybe we can do better. Maybe we can see, let's see. Feature selection. So when it comes to feature selection, I took the 8 best performing models from performing features from recursive feature elimination, and I used those to train the models and see what happens. We see that it is performing much better than basic models, but it performs slightly worse than ensemble models when they have the full data set. But it is good to understand why that happens or what that happens. One question might arise about the utilization of PCA. I did try PCA, but it did not work at all, even with high variances. That's probably because of the fact that most of the features in the dataset do not have very low variances. So even so PCA does not work that well with this dataset, and most probably should be avoided. Uh, it is very difficult to separate the data into planes, so to speak, or its principal components. And then finally, this is like a new approach that I'm like applying here, which is called SMOTE. So SMOTE is a sampling technique which allows you to sample the data, like oversample or undersample. Here I have used oversampling. So what oversampling does is for the minority class, it will create more samples that behave, so to speak, like the samples already present, which allows us to balance the classes out. That is very useful. So we can apply smooth to the training data, not the testing data, obviously, and then we can see what happens. It is difficult because given the 16% presence of imbalanced class, but it is a valid approach and should be applied when you're dealing with imbalanced data that is very resistant to being classified correctly. Which brings us to the results. All of these classifiers are from sklearn, except for gradient boosted, which is XGBM, which is compatible with scikit-learn anyways. And so these are all sklearn libraries that are directly applied. So we have 4 tables. The first one is basic. You'll notice that the accuracies are quite high. We're not going to look at accuracies. They're kind of useless. We want to ensure 2 things. We want to make sure that the recall is good, the F1 score is also good, but the precision we ideally don't want to take a hit either. Like, the better. It works for everyone. So very clearly, you can see that basic models are not performing up to par compared to the ensemble models. But what is interesting to note is that the 3 graphs look almost the same. Like an ensemble selected and small look quite similar in terms of performance. So what gives? Which is the best performing model? I have a table on the next slide that will help us quantify those. But the interesting thing I would like to note here is that you might see the selected column, which is for selected features. You will see that the precision there is overall quite much higher than it is in smooth or ensemble, which indicates that if you use fewer features, you're going to have better precision. But you are losing out on your F1 score and your recall, unfortunately. So maybe not. One solution later on down the line might be to use smooth on some models, use selected features on other models, and just use plain ensemble and then put all of them in a voting classifier. But that is a level of fine-tuning that I would ideally prefer to do if I had more data rather than just 10,000. But yeah, those are some other external approaches you can take even apart from these 4 steps. Like if you were like actually trying to like develop a model that has very good recall for the attritic class. But and so the results. So lots of results up here because lots of testing done. But if we look at it, so the voting classifier is using random forest, gradient, ADA, and bagging in a soft class voting method to get the best results, and using ensemble classifiers as part of the voting pipeline actually does do quite well. But the thing is that gradient classifiers or the gradient boosted classifier, it it on its own has surprisingly good performance. If you look at it just on its own in ensemble, gradient boosted has a 95% F1 score average and has a 90.37 recall. The 95% F1 score is impressive. But but when we look at selected features, it does inch upwards slightly when it comes to recall, where it is like at 91% recall. However, the F1 scores dropped, so you are losing up on other metrics like precision. Voting classifiers is also having a very similar performance in a close second, where we see that the voting classifier in the ensemble method has a 91%, 91.4%, which is higher than the gradient boosted for ensemble. So that is the best model if you're looking at recall. Not F1, even though it is quite close to gradient. And when it comes to smooth, all of them don't perform quite as well. It's again a bit over the place. Like you might notice that the gradient booster did not experience any improvement at all, but that is also very likely because of how the models behave. And you'll notice that like all of the models except for I believe the bagging classifier and yeah, the bagging classifier is the only model that has changed slightly. Otherwise, that's where the voting classifier has very similar results. So the bagging classifier is the only one that demonstrates a significant improvement when using the smoke method. But that doesn't mean we should dismiss smoke classification because smoke sampling has been shown in multiple papers as well to be a very good way of dealing with imbalanced data. Hence, and maybe not dismiss it, it's a good approach. So here we might say that gradient boosted or just a Voting classifier, which encapsulates gradient boosted, is in the ensemble form is a model we could be using when it comes to classifying this data. That brings us to the conclusion. So we performed data analysis where we looked at the kind of data we have, the properties of data, the distribution of the target label in the data with the variance. We then performed feature selection to identify which features are the best to use for detecting the target label, the problems with the data with its low variance, the possible solutions, the best features, and then we did machine learning where we applied ensemble learning, where we took up a bunch of which is ensemble modeling, bunch of models together, and we tried sampling where we use smooth sampling, which is better than just naive sampling where I just randomly duplicate points, which don't really help. So that's the approach, and that is all for my final project. I hope you found it interesting, and that will be all.